Once around globular clusters. So globular clusters look like this. This is a typical one, Messier object number 54, that Messier catalogue of things that are not comets, created by Charles Messier, the great comet hunter, who was being pestered with people reporting fuzzy blobs in the sky. And so he made a list of things not to bother checking. And we now use that as a catalogue of interesting objects. And quite a few of them are these globular clusters, starting with perhaps this one, Messier number 54. It's a group of stars, 100,000 to 500,000 stars, all packed tightly together, and they look absolutely beautiful with a small telescope. But there are two types of star clusters that you find: open clusters and globular clusters. The open clusters have lots of young, hot blue stars and are fairly loosely packed and fairly weakly held together by gravity. In fact, over time, the stars will slingshot each other out of the cluster, and the cluster will dissipate and boil away, with the individual stars ending up orbiting around the galaxy on their own. Globular clusters, on the other hand, consist of old stars, mainly yellow and red ones, and they're very, very tightly packed together. The reason that the stars are mostly the yellow, orange, and red colors is because they are old, and because all the really hot white and blue ones have already burnt out and died, and no new ones have been made. So open clusters, young, very recently formed, contain lots of giant stars, high mass stars that can be blue hot or white hot, but don't live very long. Whereas the old globular clusters just contain the very long-lived, fainter, low-mass stars. Now we find them surrounding the galaxy. We have about 150 globular clusters around the outer parts of the Milky Way galaxy itself. So there's a diagram here of the 100,000 light year diameter of the Milky Way, with the bulge in the center and the galactic disk, and then the globular clusters strung out around it. And that positioning of the globular clusters was a key part of what was known as the Great Debate, and the attempts to argue as to whether or not the Milky Way galaxy and its environment was the entire universe, or whether there were other island universes beyond, things like the Andromeda Galaxy or the Andromeda Nebula as it was known then. And indeed, its identity as a separate galaxy of stars was very much the subject of the debate. But this little plot here is Harlow Shapley's distribution map, showing the position of the sun in yellow and the distribution of globular clusters as all of the little green blobs, showing that they're very much off to one side. And that is because, of course, the galaxy is offset from the center to the sun is about 25,000 light years. So the galactic center is where the red cross is, and we are offset over to the left there, about halfway from the center to the very edge of the galaxy. And it shows that the globular clusters are very much distributed around the center of the galaxy. Now, when we are talking about these old stars, we're talking about ones that formed early in the life of the universe, and we identify these as population 2 stars. They are mostly composed of hydrogen and helium. They don't really have very many of the heavy elements at all. Those are formed in stars and thrown out into the cosmos to reform again in later generations of stars by explosions, supernovae, and planetary nebula, puffing off their elements that they've made out into the interstellar regions. And so really the universe is getting dirtier and dirtier. But when we look at these very old stars in the globular clusters, they were formed at a time when the universe hadn't really had a chance to produce very many of these heavy elements and forge them into new stars. So they are population 2, almost pure hydrogen and helium. Now, another way to look at the stars is to plot what's called the Herzsprung-Russell diagram. In this, we plot the absolute magnitude, the power output of the star up the y-axis, and we plot the color or the temperature, which tells us the color from the cool red stars, orange, yellow, and then all the way up to the blue stars for the hottest ones. And this chart's got some green ones on, and it really shouldn't have, because there aren't any green stars. That's the subject of another one of my lectures. Those ones should really be showing up in white. But the point is that the color tells us the temperature, and we get this line across the center of the normal main sequence stars, the ones that are forging hydrogen into helium in their cores. We have other groups of stars, the giant stars, the supergiant stars, and the white dwarfs shown here, which are the result of different processes. So the giants and supergiants are where the evolution of the star has gone beyond the core hydrogen consuming fusion process through to fusing other elements, either in shells around the core or directly in the core themselves. And then the white dwarfs, those are dead stars. They are stars that have come to the end of their life, mostly from smaller stars, and have collapsed down, puffing off their outer layers in the process. And when we look at this diagram for all the stars in the Milky Way, we see stars in all these groups. We see young, hot, blue, vigorous stars at the top left, long-lived, slow red dwarfs down at the bottom right, sun-like stars in the yellow region in the middle. We see red giants, orange giants, yellow giants. We see supergiants, and we see white dwarfs as well. But when we look at the same chart drawn for a globular cluster, it looks rather different. What we usually find is something like this, where the main sequence has some stars in it in the G and F classes, the yellow ones, and correctly drawn the white ones here, where we have a sudden turn off. The stars then seem to boil off up right and over towards the giant branch region. And what's going on here is that as time has gone on, the stars have run out of fuel in their cores. They depleted the hydrogen and left an inert helium core, and as a result turned onto the giant branch. And the most massive ones have done this first. Following them, you get the slightly less massive ones, and you gradually work down the mass scale with each progressive group of stars turning off as they reach the end of their lives. And of course, the massive stars live fast and die young. They burn hotter and at a prodigious rate. So they're the ones that run out of fuel first. And what this is showing is that the time since the stars were formed corresponds to the age of the stars at the turn-off point. And the turn-off point will gradually work its way down the chart. So if we came back in 1 billion years from now, the same globular cluster would have yet more of the stars turned off up to the right, and the main sequence line would be even shorter. So essentially, this turn-off point shows the age of the cluster. We can know the age limit for stars of a certain mass being on the main sequence, and where that corresponds to the turn-off point, that tells us the age of the cluster, because all the stars in the cluster were born together, so they're all the same age. And so this is very much a sort of way of identifying how old these globular clusters are. Whereas the Milky Way has a much wider selection of different ages of stars. There have been many generations of star formation that have gone on to making it up. So what we find is that as time goes forward, as we say, we start with a complete population on the main sequence when things are very young. And then as time goes on, the ones at the top left, the massive, hot, fast-burning stars, do their turn off to become giants. And then on the right, that gradually, that's like a fuse burning down. The stars progressively depart off to become giants from the tip of the main sequence as it gets older and older. Now, what that leaves us with is a few oddballs. We have the blue stragglers. You can see just a few blue stars in the B category over on the left-hand side of the diagram. Now, these should have burnt out by now. There shouldn't really be any blue stars that were formed with all the others at the beginning of the cluster and still around now. And there's a real puzzle as to what's going on here. One suggestion is that these are actually rejuvenated stars as a result of mergers. So where you have had a binary star system with perhaps a couple of stars, one of them has aged and swollen up into a giant and then dumped material from its outer layers over onto its nearby companion, giving that companion a dose of extra hydrogen fuel, increased mass, and suddenly caused it to burn much faster. So it's not been burning hot and blue for all its life, but it's just received a new injection of fuel. And sometimes this can result from the merger of stars where they have collided with each other completely, and two small stars have gone to make one massive one that's now burning much more vigorously. So we think those are possibilities for where the blue stragglers come from. But returning to the globular clusters, we can see that there are often two types visible. We have the ordinary globular clusters and what's known as core collapse clusters, and you have an example of each on the screen here. The core collapse one is the one at the top, and the more open one is the one at the bottom right, where you can see a more gradual progression of the stars all packing together towards the center, whereas in the core collapse one at the top, there is a very dense region in the middle indeed. And what we think has happened here is that as the cluster has aged, the dynamics of it are such that the interactions between the stars can have, as a result of close approaches, you swap momentum between the stars, they swap kinetic energy. Some of the stars get thrown outwards, boiling them out to the outer regions of the globular cluster, and the others are slowed, losing momentum, and fall in towards the center, causing this core collapse phenomenon. So you end up with an aged and dense core and many more stars thrown towards the outside. And that seems reasonable, but it also means that in the center, the density is very high. And we think that as a result of stellar mergers and collisions, you also get the formation of a black hole. Pack enough material together in a small enough space, then you will, by Einstein's equations, get a region of space so curved that life can't escape from it, a black hole. And we think that these core collapse globular clusters have intermediate mass black holes in the center, perhaps 100 to 100,000 solar masses buried in the middle there. And that brings us on to another subject. These origins of these black holes can very much be divided into three classes. We have the ordinary stellar mass black holes, if you can describe a black hole as ordinary, that result from supernova explosions, where a giant star reaches the end of its life and the core collapses inwards, the outer layers are blown apart, and you end up with a black hole of perhaps 5 to 10 times the mass of our sun, forming from a star that might be 50, 100 times the original mass of the sun before it explodes. So a fraction of it, perhaps 10%, ends up in the core as a black hole, a stellar mass black hole. And then we have the center of galaxies, where you can have supermassive black holes as a result of an enormous amount of material getting together. And we have 4 million solar masses in the center of the Milky Way. And these can range from millions up to billions of solar masses. I think the record holder is getting on for 100 billion solar masses that we know of anywhere in the universe. And I've got a talk once around ton 618, which talks about one of the most massive, supermassive black holes in the known universe. But the globular clusters seem to contain these intermediate mass black holes. And there's something very, very interesting about that, which we will come back to. But let's have a look at a few clusters. Well, this is perhaps my favorite. I live in the Northern Hemisphere, and this is the best globular cluster visible from these parts. It's very, very impressive. It was one of the first deep sky objects that I saw with a telescope, a 12-inch reflector telescope just outside Portsmouth about 50 years ago, and I still remember seeing it today. And it's like a whole collection of diamonds scattered on a velvet background. That would be my very poetic description of it. 500,000 stars, 145 light years in diameter, 22,200 light years away from us, and the target of the Arecibo radio message. The radio message was beamed out there back in 1974, containing a digitized image of DNA and hydrogen molecules for scale, and of people and radio dishes and the third rock from the sun, and set out in an easy to decode manner. But it's going to take another 22,150 years before the message arrives at M13. And then they've got to decode it if there's anyone there at all. And we'd have to wait another 22,000 years for a reply. But there's probably nobody there anyway, because these are population 2 stars without very much in the way of heavier elements, no iron for the blood, no oxygen to breathe, not much carbon to go about making interesting organic chemistry. So there might be 500,000 target stars, and there's very unlikely to have intelligent life living on long-lived carbon-based planets or iron cores for making those planets or any of that. Anyway, this is M13. It's absolutely beautiful. An object that I have never seen, 47 Tucanae, is an even larger black hole-based globular cluster. This one is a little bit nearer, 13,000 light years, but it contains millions of stars. And studies of it have shown 21 blue stragglers in the core, so some of those mergers going on in there, not surprisingly. X-ray sources, cataclysmic variables, millisecond pulsars, all sorts of interesting things in 47 Tucanae. And again, a compact core pointing at that black hole, probably 1,500 solar masses for the intermediate mass black hole in the middle. And surveying for transits of exoplanets orbiting round these million stars, we've found none, again confirming that these ancient globular clusters may not have the building blocks to make planets. They should be able to make gas giants, though. So maybe we should be finding planets. Interesting. And then there's Omega Centauri. Classed as a globular cluster, this would be the biggest of all, 15,800 light years away, visible from the southern hemisphere, so bright you can see it easily with the naked eye. You can just about make out M13 on a really clear night, but Omega Centauri much brighter and a lot bigger, 10 million stars, 4 million solar masses, so much larger that it's bigger than all the other globular clusters. And there's reason to believe that it might have a different origin. Probably, and I think this is extremely likely, this is in fact the nucleus of a dwarf galaxy. It's probably got an intermediate black hole in the center, and there's some evidence for that as well. But at 10 million stars and 4 million solar masses, this is pretty chunky and points to its origin as a dwarf galaxy. Another interesting one is the Intergalactic Wanderer, NGC 2419, in the constellation of Lynx. This is much further away, 300,000 light years further away than the dwarf galaxies of the Magellanic Clouds that orbit round the Milky Way. And at one time, it was thought to be a proper intergalactic wanderer, free of the gravity of the Milky Way. But it could now look like it's actually just captured by the Milky Way's gravity in an orbit that's going to take it 3 billion years. That's a long orbit. We have found a globular cluster that orbits the dwarf galaxy, the Large Magellanic Cloud. So NGC 1854, 135,000 light years away, is in orbit round the dwarf galaxy, the LMC. So they can have globular clusters just like we can, and so can Andromeda. And we have found around 400 such clusters. So it looks like the Andromeda galaxy's got even more globular clusters going around it than the Milky Way. And that would make sense because it's a slightly bigger galaxy. If we've got 150 globulars, Andromeda's got 400. We have about 400 billion stars. Andromeda has about 2.5 times that, about 1 trillion of them. So these seem to be in rough proportion. That makes a lot of sense. We found globular clusters going around M87, the giant elliptical galaxy in Virgo. And this one has about 13,000 globular clusters going around it. And it's likely that M87 grew up cannibalistically by eating other galaxies. Other spiral galaxies coming too close to it would be gobbled up by its gravity. And maybe its enormous pile of globulars are the previous property of those spiral galaxies that it has devoured. So that seems quite likely as well. Now, when we look at our Milky Way, one of the things that has been discovered is a whole lot of stellar streams. There are about a dozen of these that we know of that are great loops of stars that sweep around the Milky Way, through it, above and below the plane at different angles. And these look like they are the shredded remains of the Milky Way capturing and consuming dwarf galaxies over its history. And it seems extremely likely that the big galaxy has grown by absorbing and gobbling up all of these smaller galaxies. And that is basically how galaxies come to be in the first place. They grow by eating smaller ones. And that makes sense of the Herzsprung-Russell diagram, with the fact that we have stars of so many different ages. And the reason is that a lot of them have come from other dwarf galaxies and were formed at different epochs. So we have a complete mixture. Whereas the globular clusters themselves are all of the same age, and so we're all formed together. And one of the things that brings this all together is the Sagittarius dwarf galaxy, discovered in 1994 by Irwin and Gilmore. What they found was that there is a galaxy, a dwarf galaxy, in the process of being eaten by the Milky Way. And so what we detected was this stellar stream looping around the galaxy, but it's not just a continuous stream of stars. It's actually structured to it, and it has the nucleus of this Sagittarius dwarf galaxy still in existence. And right slap in the center of that galactic nucleus of the dwarf is a globular cluster, Messier 54, the one that we started this talk with. And what this is telling us is that that globular cluster may well be the original nucleus, the original core of the dwarf galaxy. And this would bring it all into some sense. There's another picture on the left there of a a globular cluster, Palomar 12, quite a small one, that appears to have been captured from the Sagittarius dwarf. So even these dwarf galaxies probably had them before they came too close to the Milky Way and got spaghettified. But one of the things that we know about galaxies in particular is that they all have these supermassive black holes in the center, and there is an amazing correlation between the mass of the black hole and the mass of the galaxy itself. And if you plot the two against each other, you get an amazing straight line all the way from the biggest galaxy with 1 trillion solar masses and 1 billion solar mass black hole, so 1/1000th being the ratio, and that ratio is maintained so that a modest-sized spiral galaxy might have 1 billion solar masses and a 1 million solar mass black hole. But the straight line continues, and the globular clusters, where we have been able to determine the mass of the cluster and the mass of the black hole, the intermediate mass black hole in the center, we are finding these sit on the line as well. And it all points to the fact that actually these globular clusters really are the nuclei of dwarf galaxies. And maybe those globular clusters that we have orbiting around us are those nuclei. They've lost their outer layers because the gravity of the Milky Way has stripped all the stars away from their outer regions where they were less tightly bound, and only the tightly bound cores survive with their intermediate mass black hole controlling them in orbit around the outside of their main galaxy. And eventually maybe they will get swallowed up as a result of some perturbation, but it seems extremely likely that globular clusters and dwarf galaxies are really very, very highly related, if not one and the same thing, and that we've been staring at this all this time and not really realizing what we were looking at. And so with that, I will end this talk. Thank you very much for listening, and hope you enjoyed this one. This was created as a result of a number of people commenting that they would love me to talk about the Omega Centauri and the globular clusters in general. So I hope I've answered the questions on that one. Thanks very much.